Good afternoon, everybody. Welcome to our afternoon Geo-Institute sessions on the final day of VTech. Thanks for sticking around. We have a couple of great panels for you this afternoon. I'm Geo-Institute Director Brad Keeler. A unique part of being a civil engineer and a geotechnical engineer is being there during and following disasters to help rebuild and to mitigate and prepare for future disasters. In May of this year, about an hour and a half from where I grew up in mid-Michigan, the Edenville Dam failed, which then caused the overtopping of the Sanford Dam downstream. Members of the Geo-Institute Embankments, Dams, and Slopes Technical Committee visited the area about a month later and started work on a report about the failures. We're fortunate to have much of that reconnaissance team with us to present today. Tim Stark, the chair of our Embankments, Dams, and Slopes Committee, will be moderating our panel today, and I'll let him take it from here. Tim, thanks for putting all this together.
Great, Brad. Thanks so much. And in 2019, the Embankment Dams and Slopes Committee submitted a proposal to the Geo-Institute to fund field reconnaissance events of embankment dams and slopes after extreme events. Of course, embankment dams and slopes are important for public safety and societal resilience, so we thought it would be good to learn how these structures perform during extreme events and help us improve our design. The Geo-Institute funded our proposal, and we are able to conduct 2 reconnaissance trips per year. We use the funds for younger members of the EDS committee, and so they get to come along and gain experience. So the Edenville Dam is our first trip, and it occurred in May, the failure. This is a slide that shows all the team members for the reconnaissance team. Daniel Pradel of The Ohio State University led the reconnaissance team. He's going to lead off. Alan Esser of SME Inc. is going to contribute. Colin Brooks from Michigan Technological University. Marin Clark from the University of Michigan. And Dimitrios Zekkos from the University of California at Berkeley will present the findings that are in a over 200-page report that will be published by ASCE as a geotechnical special publication. Daniel, thanks for leading the team.
Thank you very much. Edenville Dam is an earth dam that was built between 1923 and 1924. It was built for flood control as well as hydropower generation. In the lower left, you see a picture that was taken in July 30, 1924. The earth dam is almost reaching its final elevation. The power plant and the spillways are under construction. And the lower right image shows the earth dams having been completed, as well as the spillway and the power plant. Something that is relevant about these years, 1923 to 1924, is that it was before the soil mechanics principles pioneered by Carl Terzaghi were widely known in the US, and it's also before the quality control measures for soil compaction were proposed by Proctor in the 1930s. In terms of setting, the Edenville Dam, was built at the confluence of 2 rivers, the Tobacco River on the west, and the Titabawasi River on the east, and together they form the Wilcox Lake because of Edenville Dam, and the dam is crossed by M30 highway at the site. Here is a view looking south where you see both rivers. You see the lake, Wilcox Lake. You see the M30 road highway as well as the bridge, and the 2 spillways, one on the Tobacco River side, one on the Titabawasi River side, where also the powerhouse was located. The failure took place where the yellow arrow is located, between the powerhouse and spillway and the left abutment of the dam. The total length of the dam for scale is about 2 kilometers, 6,600 feet, and it had a maximum height of 54 feet or 16 meters. What is particular about this failure is that it occurred during the day and was captured on video. Here you see the failure taking place. And also through Twitter, we have the exact location of the videographer. That is also helpful. After the failure took place, the dam breached and water started escaping Wilcox Lake. And also we have another video taken from the air about an hour later that actually shows us how the breach rapidly enlarged and started sending waters downstream towards Sanford Dam and Sanford Lake. The Edenville failure prompted the evacuation of about 11,000 local residents. This happened amid the COVID-19 pandemic. And as the Sanford Lake started to rise, very quickly Sanford Dam began to overtop, as you can see on the lower left of the image. This is Sanford Dam, which was built at about the same time using the same techniques as Edenville Dam. And because of overtopping, the dam was completely destroyed. These dam failures resulted in devastating consequences in the local communities, Edenville, Sanford, and Midland, and many houses were removed off the foundations. We had a large amount of flooding and devastating consequences for many of the local residents. Alan? Alan Esser of SME will be providing more about the setting of Edenville Dam.
Yeah, Daniel, move on for right now.
Okay. So, well, let me use some of his slides. The dam is one of a series of dams that was built by Frank Wixon. And we have some cross sections telling us how Edenville Dam was built. It had 2.5 to 1 slopes on the upstream side and 2 to 1 slopes on the downstream sides. This is a drawing made in 1923 by the original designers. In many of the pictures that we were able to obtain, we see some of the techniques. It looks like a large amount of the material to generate the earth dams was obtained by horse-drawn scrapers. You can see a few in this picture over here on the right. And as I mentioned before, this was before the Terzaghi and Proctor contributions. The drains in the dam were vitrified clay pipe that was placed loosely with loose joints along the foundation soils. So in terms of consequences, we had loose permeable fill, poor or no foundation preparation, debris in the fill, and a homogeneous embankment. That means a dam without a clay core that was actually built. In some of the aerial photographs, we see evidence of the use of scrapers, like these finger-type marks between the Tabaco River side and the Titabawasi River side. And we took samples that were tested in the lab that allows us to obtain permeability, strength, densities, and many of the other properties in the soil. Some of these location of these tests are shown in this photograph here, where S1, S2, S3 are our bulk samples. We also took a Shelby tube at location S1, and we did the strength testing by direct shear method. This is one of many floods that have affected the area. And here you have some of the different discharge rates, but it doesn't look like the reservoir reached that elevation that we saw in the video a moment ago before. In terms of accumulated precipitation, we have some stations in Midland, but we also have some stations that are in the area north of the dams, and the precipitation appears to have occurred in the 2 days prior to the failure of May 19th. The dam hazard was considered high, and sometime before the failure, the FERC had removed the certification of the dam. Next, Marin Clark is going to talk about the geology and the geophysical testing. Go ahead.
Great, so I'm going to discuss the geology and geomorphology studying of beneath the dam, as well as the geophysical properties of the dam and foundation materials. This was based on field work done by myself and my colleagues, Nathan Nimi and Dimitrios Zekkos, as well as a whole team of graduate students who were restless and desperate to escape their isolation during the pandemic. So next. So the first thing I want to point out is that the Edenville Dam was constructed in an area of really locally complex topography. And so you can see in the LiDAR elevation map on the left-hand side, this area in green, shades of green, represents the entire river valley of the Tittabawassee River. And in the white areas and lightest green shade, that sinuous shape that we can see in the upper left of the image, we recognize that feature as the active channel. In the darker green and yellow-green colors, we also recognize a number of flat surfaces that occur parallel to that active channel. And with those features, we recognize former river levels of the Tittabawassee River that would have existed hundreds to possibly even thousands of years in the past. And so in the right-hand photograph from a drone, we can also recognize one of these terrace levels, seen by the dark black color in the foreground on the left-hand side of the picture. This is one of the surfaces of these ancient river levels. Next. So based on the topography and on the field observations, we can make a map like the one on the left and describe the sequence of terraces and river levels that exist in this area. They're done chronologically from youngest T1 up through oldest T6, and those also follow the lowest to highest elevations. In the right-hand photograph, you see a picture of one of these river terrace levels. And importantly on it, we see a preservation of the soil and organic horizon with those little spikes that you can see in the picture, being the remnants of drowned trees and other vegetation. So this tells us two important things. One was that there was no significant removal of the original surface prior to the dam construction, and also that there was not a significant amount of burial of sedimentation happening following the impoundment of the lake. Next. Importantly, we also recognize that that vegetation was burned and leaving pieces of charcoal and other remnants of burned vegetation in the terrace levels. And so from that, we surmise that the vegetation was burned as a way of clearing the area prior to the construction of the dam. So next. So those terrace levels and the flood scour exposes a layer cake stratigraphic sequence of the materials that are directly below the dam. And from that, we recognize three main environments of deposition. So primarily, the materials are made up of glacial deposits related to Quaternary age, deposits of the Saginaw lobe of the Laurentide ice sheet. And then unconformably on top of that glacial sequence, we observe fluvial sands and then the buried soils and drowned vegetation I mentioned earlier. Those are of unknown age, but stretching certainly into the modern time, right just prior to the construction of the dam. Next. And so this is a picture of the lower sequence of the glacial tills. And we recognize 3 different conglomerates units. These are matrix-supported conglomerates with pebble to boulder-sized clasts. We interpret these as lodgement tills. Locally, we see observations of very thin, only locally indurated pea gravel and sands, which we interpret to be glacial outwash. Next. Above these 3 sequence of lodgement tills, we see that the sequence is capped by a reddish brown clay silt deposit that lacks sedimentary features, and we interpret this deposit to be a lacustrine deposit or a proglacial lake. This unit was similar to pieces of reddish clay material that we also found mixed into the dam deposit. Unconformably, back, Daniel. Unconformably on this sequence, we see fluvial sands and flood deposits related to the breach itself. Okay, now next. So we can correlate the stratigraphy to interpret the geologic conditions at the base of the dam, primarily through 2 exposures on either side of the breach. So on the left-hand side, you see a close-up of exposures in the left abutment. And importantly, we can trace the surface of terrace level T2 with the vegetation and burned vegetation layer directly underneath the dam deposits. And we recognize that as an original layer through the bioturbation, vegetation, and tree roots. We also see charcoal in the dam, which suggests that the dam materials incorporated the burned vegetation nearby. We also see the burn layer exposed in the spillway exposure in the right-hand photograph here. Here, that charcoal and vegetation layer is on top of terrace level 3 or T3, and it also exists directly beneath the dam toe. Next. So these field observations and allow us to construct a geologic and topographic profile from beneath the dam. And the first thing I want to point out to you is the stepped profile, which causes the dam thickness to vary between 6 and 16.5 meters. And that stepped profile is directly related to the different terrace levels over which the dam was built and does appear to be undisturbed prior to the dam construction. The dam was built primarily on glacial till deposits and only locally on outwash. Next. So here, importantly, I just want to point out a correlation of the location of failure, which is shown in the left-hand picture here, which is a topographic image shown, the failure location shown by the red line with the Roman numeral 1. And Dimitrios is going to talk a lot more about how that position was located in the next section. But here, I just want to draw your attention to the fact that it correlates with a change in elevation from the T3 to T2 riser. That's the step in topography between the terrace level 2 and terrace level 3. So that projects right into the location of the dam at failure. Okay, next. So we also conducted a number of geophysical surveys along the northwest of the spillway, along the intact portion of the dam. We conducted seismic and resistivity surveys, both a P-wave and MASW survey using a hammer source and an electrical resistivity tomography survey in the same position. Next. This is a summary of our seismic results, and we observe generally very low velocities within the dam materials with a very sharp contrast to higher velocity materials at about 12 meters depth, which is in good correlation with our topographic profile estimates of the dam fill thickness. We see both low velocities in P wave as well as surface waves, consistent with the low density materials inferred from the material testing. Next. And finally, this is a summary of our ERT tomography results. And again, we see first order, a contrast between high resistivity materials shown here in magenta and yellow over very low resistivity materials shown here in purple at about a depth of 15 meters. And this is also consistent with the observations of the dam materials as being mostly dry, poorly sorted sands and silty sands overlain over clay-rich till deposits of glacial origin and also likely to be saturated. Okay, next. So in summary, for the conclusions of the geologic and geophysical testing, I want to point out that the complicated topography exists beneath the dam due to the fluvial terraces, of which that topography may have contributed in some way of the localization of failure where it occurred. Second, that we observe a burn layer that suggests that the forest vegetation was not removed, but rather burned and left in place prior to the construction of the dam. And then finally, the geophysical attributes of the dam are consistent with the testing results. That is, that they're low density material properties that are rather homogeneous in nature. Thanks.
Colin? All right. Next, we'll have Dimitrios, who will be telling us about the UAV characterization of the dam.
Hello, everyone. It's a pleasure to talk to you today. I would like to acknowledge the contributors to this aspect of this work from UC Berkeley, University of Michigan, Elxis Group, and Indiana University. Also, Nathan Niemi and John Manusakis were helped on the aspects that I will present on the digital image analysis. Overall, along with Michigan Tech, and unfortunately they have a technical problem, so they will not present today, we all deployed a number of UAVs at different times and with different sensors. What I'm showing here is that basically Indiana University had a UAV with LiDAR, and we also, from our team, we deployed a UAV with optical cameras and infrared cameras. These sensors were used to collect data and create 3D models of the dam and the area around it, as well as try to characterize material type and moisture conditions. Next. What you see here is a flyover video of the Edenville Dam created with UAV imagery using the structure from motion technique. This was also something we're going to be discussing in a bit more detail, so maybe I'll present it now. The structure from motion technique, for those of you that are not aware, is basically a digital photogrammetry technique where we collect with the UAV overlapping photos of the target, in this case the Edenville Dam, and we're stitching them together in the digital space to create a 3D model such as the one you've seen here. Now, the model you've seen here is basically a high-resolution model. It has each pixel is about 1 centimeters, and so you actually can see very significant detail. And also, it's important to note that you're able, on top of that model, to overlay other data, such as the infrared data that I will also present later. Before the UAV with LiDAR by Brian Yanaitis and the Indiana University was very useful because, along with the structure from motion technique, it allowed us to have a second view of the elevations that are involved after the failure. So you see the figure to the right is a figure of the elevations involved. And because LiDAR data was available at this site before the failure, we're able to take the difference between the two models and look at where sediments were removed due to scour during the failure, and where also they were deposited. And I don't know if you can see it on the lower left figure. This is a picture showing that. We had a few meters of scour of the native material on the downstream of the dam after the failure. Next. We also fused data, the optical data and the infrared data that we collected. The figure to the right, on the left of that figure, you can see an orthophoto, so a photo that has accurate dimensions and actually in 3D space of the Edenville Dam. On the lower part of that photo, I'm hoping you can see the bridge section. And to the right of that figure is a similar orthophoto from the infrared data. Basically, that gives you temperature of the ground or whatever the target is at that time. Using this information, we're able to see different materials, concrete versus soil, sands versus clays, and also look at how wet the material is. Next. This is an example of looking at how the infrared data is useful to look at the wetter areas. We are on the downstream side of the dam, close to the spillway. And actually, you can see near the toe of that dam, there is actually seepage coming through. If you click one more time, Daniel, that you can maybe see visually. You can definitely see it when you're at the ground, but it's really, really easy to see when in the infrared imagery. Basically, what you see there is where the water is coming out of the dam. You can see it as seeps, and they're shown as lower temperature material because it's wetter and the water actually in some cases it's flowing, so they become really visible. We applied the same technique on characterizing the remaining exposures of the dam in the bridged area. And we had the northwest exposure and the southeast exposure. This is described in detail in the report, so I won't go to every single detail here. But one thing we're able to see is look at material and separate between clay and wetter soils on that exposure versus coarse grain, sandy and drier areas. And that information was mapped in a remote manner, but then was also confirmed by the team with visual observations. Now, one thing that we had the benefit of in this project was there was a pre-failure LiDAR data set that was collected in 2017, so basically 3 years before the failure. One thing that is interesting to note is when you look at this LiDAR data set, on the downstream side of the dam, there are two lineaments that I'm hoping you can see in the photo of two features that are really visible on the slope inclination photo imagery. On the left, that is shown with grayscale, that shows how inclined the ground is. And the right figure shows the slope aspect, the orientation of that slope. And you can see there are these two features that are standing out, although the remaining of the dam really is kind of very uniform. One of the two locations, the lower one in this figure, is coincident with the failure location. We also took advantage of the failure footage that all of you have seen and Daniel presented earlier to better understand, first of all, where we are, where the failure is taking place exactly in the dam, and we did this with a 3D image projection, and also look at the failure kinematics, exactly how things moved during the failure, and I will describe that next. The figure on the right shows examples from our reports on how we illustrations of how we calculated the location where we are, basically using that footage and information we have from our own 3D model. We're able to look at features and pinpoint, I will say with high accuracy, exactly where the failure happened. The figure on the bottom left is a photo that was available through CNN after the dam has been breached and is basically being washed away. And we use that information in identifying exactly really what happened during the failure. Next. Now, if we overlay the evidence that I've shown and the team has shown before, first of all, this is the geometry of the dam before the failure. The red line is our best estimate of the failure location based on the video footage. The two green circles are the two lineaments that I mentioned, the two in the slope aspect, and the slope and the aspect of the dam. So the two features that seem irregular. On top of that, there is also insert data that was made available online by a different team. This is Ovela 59, it's a company. And we show that here with a blue color. And you can see how all three is very coincident. On top of that, actually not on top, below that, there is also the steps between terrace 2 and terrace 3, which we don't really know where exactly it was reflected in our dam, but you can see our projection based on the existing information. We cannot really project that anymore just below the dam because all the material has been eroded at that location. Next. So this is observations from video, which will be discussed in more detail by Daniel next. But one thing I want to mention about this video that I think is important is when this footage that is available online was collected, at the top right side of that figure, of that image, you can see that the crest of the dam has already depressed some, and so the video starts from that point and on, okay? And what we will do in the next slide is we actually stabilized the image so that we collected the footage from on the internet. We stabilized the image to make it more stable and look at the same things on the same location. And then did what we call we applied pixel tracking algorithms. And so in the next slide, you will see some pixels on the right figure. If you go to the next slide, Daniel. We have 5 pixels that we're tracking here. We did a little bit of slow motion of the video, and we're tracking exactly how the failure happened in the location of these 5 pixels. And of course, you can do that with more pixels, but those we think is enough for us to understand what's going on. There's a 5th pixel that is lower than the 4th pixel over there and was never moved. Daniel, if you can go back and front one more time to play the slide again. From that information, it's not qualitative at all. You are able to calculate horizontal and vertical and total displacement at the location of each pixel. This is shown to the left. And since you know you can calculate displacement and you know the time it takes, you can calculate also velocities in the X, Y, and total in the total direction. Next slide. So conclusions from that digital image analysis that again are described in more detail in our report. The movement that you see, I hope you agree, is consistent with the rotational type of failure. The failure is located entirely in the dam, doesn't involve the subsurface, at least what we see in this footage. There is water jets, and this we'll discuss later, but there is water jets. Water is squeezing out of the mass as it's failing. And finally, the failing mass is found to, of course, gradually accelerate, reach a velocity of up to 5 meters per second based on our estimates from the previous analysis. And once that mass fails, it becomes stationary, it stays there, and there are about 5 seconds from that point on until water starts coming in. So it's not like water came immediately after that failure. There are 5 seconds indicating that a small portion of the dam was still present behind that failure. Putting all this information together, we have generated these cross sections. I show here two models. This is the location of the breached area. I show here two models because there is some uncertainty about what the original ground surface is and whether we're sitting on terrace 2 or terrace 3. But we can focus for the most part on the top model for now, which assumes that we're still staying on one terrace. What you see with the green line is the the pre-failure LiDAR. So it shows the geometry of the ground surface and the dam before the failure. The red and cyan lines shows the post-failure LiDAR and structure from motion models. There is a small difference between them, but they're very, very similar, I would say. And you can see that those are below the previous ground surface, indicating in significant scour of at least 2 meters in the downstream side. On the right of that figure, we also have the typical lake levels for the winter and the summer season. These were actually controlled at that level. So this is what the variation was. And you can see the top elevation is the water level at the time of the breach based on the field data that was collected in the field during our reconnaissance. And finally, on that image, you can see overlaid the pixels that show how things moved. And our best estimate failure plane, the basal plane of the failure mass based on the information we have. And with that, I will stop here. Thank you.
This is Daniel again, and I'll be talking now about the failure modes.
And Daniel, this is Colin. Can you hear me now?
Yes.
If there's still time for me to go through my slides, I'd be happy to do that.
All right. Let me go back. Welcome back, by the way, Colin.
Thank you. For some reason, I couldn't get promoted to a speaker while logged on as Windows, so I'm using my smartphone right now.
Yeah. I normally blame it on Bill Gates, but I don't think it's appropriate here. All right.
Thank you. Yeah. I'll just talk quickly about how we used structure from motion close-range photogrammetry to derive 3D models of the flood impact sites from the UAV imagery that we collected. Next slide. So in the 3D data creation, I said we used structure from motion. This is software that matches key points in stereo overlapping. It's a process that includes software that matches key points in stereo overlapping UAV photos. The software that we used was Agisoft Metashape, which is one of the Pix4D is the other probably best known software. And in the software, in the structure for motion process, it estimates the 3D scene geometry, produces scaled and georeferenced outputs. And the primary outputs that we use are the ortho photos and a digital elevation model. And as was just shown, if you're in an area where canopy penetration is not important, this can be a high accuracy and less expensive alternative to LiDAR. And there's more information there in that Karavik 2016 reference about structure from motion if that's of interest. And on the right are some of the input images, including some of the field photos. And we took those photos every few seconds in order to create the stereo overlapping imagery needed. So here's a result from the Edenville Dam output location. And on the image on the left, you can see the pre-failure image from an Esri base map, an ortho photo in the middle, and the digital elevation model with a hillshade effect on the bottom. And what we did is we drew a line across there in order to extract elevations at key points, and then also create a profile of where the dam used to be and where the eroded area was now located. Next slide, please. So here's a profile that we created from the structure from motion derived DEM, and those 5 points labeled on there are the same 5 points shown on the image on the right, and from that, the specific elevation values can be extracted. Next slide, please. We also flew over the M30 over Wixom Lake bridge site. So this was a bridge that was taken out during this failure event. You can see there was a Twitter image on the bottom left. Essentially, where the bridge was located became a constricted area after the dam had failed. The water was pouring through, creating a significant scour event, and it took the bridge out and removed about 6 meters of material in terms of height. Next slide, please. And then also downstream was the Sanford Dam that was overtopped after the failure of the Edenville Dam. There was about 18.5 meters of embankment erosion. On the right are ground photos and then the drone photo of the equivalent location. And you can see the areas where upstream of the dam, looking where the bottom right, where the dam remnant was and where the dam used to be on the top right. And again, the pre-failure image, ortho photo, and the hill-shaded DEM created from the structure for motion process. And here we looked at 3 different lines, one on the left, one in a center area, and one on the right in order to create profile data. Next slide, please. So these are the results from that. For example, on the western end, between the lowest point and the highest point, we saw 5.2 meters of difference. In the central area, we saw 4.4 meters of difference. And in the eastern area, where the highest point was the dam remnants and the lowest point was the new scoured riverbed, we saw 13.0 meters of difference using the DEM derived from structure for motion. And that's it for me.
Thank you, Colin. How are you?
Thank you, Daniel.
All right. So, I'll be talking about the failure modes. This is Daniel Pradel again. And Dimitrios, a moment ago, told us about the first frame of the video, where we see in particular that the lake is well below the crest of the dam. Our observations at the site showed what we call a scum line that was located about 1.5 feet below the elevation of the crest. We see a zone where there's very clearly a depression. This is the area that is going to fail in the video. And we also see a little bit of water that is able to flow down the protected side of the earth dam. During the video, we see in various frames jets of water. I've put in some circles where those jets of water are emanating from the fill that has failed during the slide movement. And that tells us 2 things. The first is that we're having really high groundwater pressures that are developing within the soils, and also that the material is contractive in nature. This was confirmed also by the low densities that we obtained from our Shelby tubes, as well as the contractive nature that we observed during shear testing. I'm going to show you the video again, where you'll be, hopefully you'll be able to see some of those jets of water emanating. But there's one more feature that we see is when the soils from the failure reach the toe of the dam, they spread in a liquefaction type manner of spreading. So let me play the video once again. And therefore, there were 2 modes of failure that our team considered. The first one was that we had a rise in reservoir elevation that resulted in additional loading, in addition to additional pore water pressures within the dam, and that caused a rotational slide. The second possibility is that the additional loading from the rise in reservoir elevation caused static liquefaction type of failure of the materials within the dam. In terms of modeling to see which one of these, whether these mechanisms were viable, we looked at how the dam was constructed. As Marin pointed out, as we've seen in the slides from Alan Esser, we have a dam that was built without a low permeability core. We also did not see any evidence of tow or gravel blanket placed within the dam. And the dam was mainly built out of sands that would be typically classified as SP or SM based on our testing. There was a system of drainage, and in the area of the failure near the left abutment, we could see a modern pipe that likely connected to the clay pipes, vitrified clay pipes that we saw in other areas of the dam. These pipes would have been placed directly on top of the natural soils, the foundation soils, and based on other engineers, geotechnical engineers, particularly here in Ohio, who have worked on dams designed in the 1920s and built in the 1920s by Holland, Ackerman, and Holland. The typical design by at that time was to put these pipes loosely connected at regular intervals along the foundation materials. And these would typically reach a point within the dam that would be around the protected side top of slope. So we did some finite element analysis. Here is the mesh that we used, and in which we not only considered the dam, but we also considered these pipes, this drainage system with loosely connected pipes that would be partially filled with sand. So here we have at the beginning of the storm, the elevation of the lake and the predicted phreatic surface that would be the dark or the thicker line that you see within the dam. And as the reservoir rose, we did a transient analysis. We have the phreatic surface that is rising. And by the time we reach 1.5 feet below the crest elevation, the phreatic surface was really high and probably reaching the face of the protected side of the earth dam. When we do calculate factors of safety with the strength that we measured during our direct shear test, we find that there's very low factors of safety for a failure of the downstream face. We have a failure that is relatively similar to the one we see on the video. And here we calculated a factor of safety of 1.08, which is obviously very, very low. Since in our finite element analysis, the dam did not fail, we were able to pursue it and look at what happened when the reservoir was lowered. And we find that the upstream face of the dam was also very vulnerable with very low factors of safety. And we did observe some failures, both when we were inspecting it, but also in the drone imagery that Professor Zekkos showed us a moment ago. For the static liquefaction mechanism, this is a mechanism that has affected in the first half of the 20th century many hydraulic dams, but that was recently highlighted by the failure in Brazil of Brumadinho Dam. And this is one area that still requires investigation, but to understand how static liquefaction takes place, one of the best sources is to look at some of the tests done by Professor Gonzalo Castro for his 1969 thesis. Here he had built a special triaxial device that allowed for stress control by mechanically putting loads on the counterweight. And for the very loose sample, which is as A in this normal stress versus shear stress diagram for his triaxial testing, what we see is that once we reach the maximum shear stress that the material can take, we have that the material cannot take anymore. The pore water pressures become very large, and we have essentially a failure that takes place. Importantly, for very loose materials where the pore pressures very quickly become very high, we do have a much lower stress ratio at failure than we would have for a slightly denser material. Here we see in the upper plot the deviator stress versus actual strain, and it took 20 minutes during this test to reach the maximum deviator stress, but it only took 0.15 seconds to go from 1% actual strain to over 20% actual strain. And here for that very loose material, the A material, we see how quickly the water pressures exploded and were induced. So in summary and conclusions, Edenville Dam is a rare case history of a failure that was captured on video and that a team, the ADS team, was able to analyze, not only using modern tools, not only being able to deploy very quickly, but also was able to supplement that with traditional geologic and geotechnical techniques. These geological techniques, for example, showed us the difference between these 2 and 3, T2 and T3 layers near the location where the failure took place. Edenville Dam failure, I think, is very important because we have hundreds, if not thousands, of dams in the U.S. that were built before modern geotechnical practices, such as the soil mechanics techniques and that were pioneered by Carl Terzaghi, but also the compaction control techniques that were proposed by Proctor in the 1930s. So many of these dams were built before those days and without the benefit of that knowledge. If we look at Michigan alone, Michigan has 271 dams that are over 100 years old, and the great majority are way beyond their 50-year design life. In terms of mechanisms of failure, we consider 2 as being the most likely, or one among 2 to be the most likely. The first one is a traditional slope instability type of failure, where we have the rise of the reservoir in combination with partially filled drains, in combination with a geologic feature at this site that resulted in conventional type rotation failure. The evidence that we see of pore pressure generation and liquefaction is the result of the large displacements that resulted in the liquefaction type spreading of the slide debris. The second possibility, which is worth investigating, is having a static liquefaction where loading from the reservoir caused static liquefaction within the central portion of the dam, and that lowering of the strength allowed the failure to take place. With that, the presentation is over, and Tim, I believe you're going to tell us about questions.
Great. Thank you, Daniel. We have a few questions here in the last few minutes. First question, and maybe this is to you and Alan. Would a cutoff wall,
Is
and
Alan here? I don't know.
he was trying to log in, but if not,
I'll take it.
you can lead and others can contribute. Would a cutoff wall installed in the 21st century have saved a dam? And so you could look at not only a cutoff wall through the embankment, but if the cutoff wall needed to extend into the foundation as well.
Well, I did some calculations in which the drain was fully functional, and I got factors of safety. I'm going out of memory, that were around 1.4. So without the water pressures, or without water allowing for static liquefaction or slope instability failure, probably the dam would not have failed.
Yep. Okay, next, how much cohesion, if any, was measured in the direct shear test? Was this cohesion used in the stability analyses?
Yes, we found a very small amount of cohesion. I can pull out the number, but I want to say out of memory, it was in the order of 20 or 30 pounds per square foot. So not a lot of cohesion. The material had very small amount of fines. And yes, we did use cohesion, the cohesion that we measure in our test, in our slope stability analysis.
Okay, and could you have used a stress-dependent envelope that did not have that cohesion, went through the origin, given the low amount of fines? And if so, what effect do you think might have that had on the factor of safety?
Well, we did when I did the direct shear testing, we did this direct shear testing with very, very low vertical pressures and relatively high pressures, and we did not see evidence of curvature. So in many ways, it's considered.
Okay. Next is, there are a lot of questions about the videos, so let me touch on that. The videos of this will be available within 24 to 48 hours. The videos of the failure, they're available on YouTube if you just Google or search Edenville Dam.
Tim, if I may say, the YouTube information, it's available on the slides. Like this one and this one. And I understand that all the conference participants are going to get a copy of or I'll be going to be able to access the video of the failure so they can have the YouTube videos information.
Yes, that'll be within 24 or 48 hours of this. Maybe last couple questions here, and we're going to have to sign off. Do you have any soil borings of the portion of the dam which did not fail?
Marin, do you want to handle that one?
Sorry, Tim, can you repeat the question? I didn't hear the last part.
Do you have any soil borings of the portion of the dam which did not fail?
So we have collected a number of samples from both the exposure at the spillway as well as the upstream embankment, but those haven't been tested yet.
Okay. Okay, that leaves 12:29. So we're going to have to sign off here. If you have additional questions, the questions are still coming in. Please email me or Daniel Pradel or any of the team members, and we're happy to respond to you. Again, the 200-page report will be published as a GSP. It is under our last review, so it'll be with the ASCE here shortly. So Daniel, thanks so much for leading the first EDS reconnaissance team. And thank you for everybody for participating.
Well, this was the greatest team that I've ever participated with, and really everybody on this slide here should be thanked.
Yep. Thank you. Okay, thanks.